Hello, gentlemen. This is an interesting container that I sort of invented. I mean, it's kind of a mishmash of some other ideas, but nobody ever put it together this way, and it has some interesting trade-offs. So I'll go through the slides and then I'll show you how it works, and we'll go through the code and I'll, upload it to GitHub. But anyway, it's like an ECS style, storing entities type of container. So the data is unordered, it's growable, it has stable pointers, it's contiguous. It has O1 insert erase, it has ON branchless iteration, and it has generations. Now, some of this sounds contradictory, but I'll show you how it kind of works. If you imagine, what would a container like this be good for? If you are in a high modification scenario, so you're constantly inserting and removing elements from this container, right? Entities and other entities point back into this container, right? So if you imagine having entities that hold pointers into this container, and the entities in the container can be removed, you're going to need a way to check if those entities are live or if they are valid. That's why I implemented generations. Now it kind of saves me one if check at some point, and I was going for fast lookups, so that's the reason I did it. Anyways, the limitations. It's on Windows and Linux only, as far as I know. I mean, it uses VirtualAlloc on Windows, and it could use mmap on Linux, though, I only implemented the Windows version right now. It has uint32t max elements, so that's like 4 billion. It uses uint32t as its skip array elements. There's a parallel skip array, which allows the iteration to be branchless without using a Boolean skip field. It's a design that's stolen, ripped off straight from Matthew Bentley's PLF colony and, standard Hive that's going to be added to the standard. They use uint16t, but since mine is contiguous, it needs to use a bigger size of integer. And I figure nobody's going to be storing more than 4 billion elements, so this is a good size. All right. Erase is going to leave holes. It doesn't compact, so you're not going to get SIMD support. The iterator is invalidated on erase due to some metadata kind of being weird, but pointers are valid. All right, the basic architecture. These statics are for like the page size on Windows. All right, the page count is obviously how many pages are allocated. The high water mark is the furthest ever allocated element. All right, so if you remove an element, it kind of turns into a free list node to be reinserted back into that removed slot. And if there's no removed slots, then you start incrementing the high water mark. All right, that's what it's used for. Anyways, these are the pointers to the data, the pointers to the parallel skip array, and the free list node pointer. Now the free list is a last in first out stack, and it's just interleaved with the erased slots. You'll see how that works. It makes reinsertion really fast. All right, why did I invent this? Well, Colony returned handles that were too large for me, right? And it doesn't have built-in generations. So why would you have a stable container, right, that other entities are going to store these handles back into this container? And this container doesn't have generations. So you're going to need to do an if alive, if generation check on Colony. But for me, you can just do a if generation check. So you're going to save one if on lookup versus Colony. Sparse set, you're going to save a double indirection. So you're going to have one indirection on the pointer in my design versus a sparse set, which is going to have a double indirection. Otherwise, sparse set has the same algorithmic complexity, but slower lookup, insert, and erase. All right, Colony is not branchless and it's not contiguous. And when I was making this container, I sort of just watched some talks on Colony, and I saw that he used a Boolean skip field, or he removed the Boolean skip field and invented a skip array that makes it branchless to iterate. And he didn't make it contiguous. So I was kind of annoyed that it wasn't contiguous. So I kind of just decided as a challenge to make a contiguous version. And then I looked into the code of Colony and I saw that the iteration wasn't branchless. He used a branch between the group blocks because it wasn't contiguous. So I removed that branch and I made it contiguous, and I actually found a lot of other benefits along the way. So, it ended up being useful to do this. All right, versus colony, my container is going to have a higher memory footprint. It's going to be branchless in iteration. It's going to be similar or better in performance. I've seen it a little slower and I've seen it a lot faster in some scenarios. All right, and the handles are a lot smaller. Versus a sparse set, same algorithmic time complexity. Like I said, the handles are stable on both of them. The iteration on mine is going to be slower. There's no SIMD support on mine, and there is SIMD support on sparse set because it's packed. It iterates just like vector. The insertion is going to be faster on mine because there's no reallocation. The erase is going to be faster on mine because there's no swap and pop. On a sparse set, if you erase in the center of the sparse set, you basically, take out that element into a temporary. Now you take the last element and put it into that erased slot, and then you delete that element. So you have to swap and pop in order to keep the array compact. Mine is going to have faster lookups because it's direct pointer lookup. Versus a sparse set, you have to do a ID to the sparse array, and then you get an index, and you look up that index into the dense array to get your data. So it's a double indirection. All right, both of them have unordered data, and both of them have 8-byte handles. Now it grows using VirtualAlloc. If you don't know what VirtualAlloc is, it's in Windows.h, and it reserves virtual address space. Virtual address space is in the operating system. There's like terabytes of it, and it doesn't actually map to any physical RAM. And then you can commit pages, and a page on Windows is like 4 kilobytes, and that'll map it to actual RAM, and that kind of goes through the processor and the operating system. It does that all for you. So as far as your container is concerned, the memory is all contiguous, and the performance is as if it was all contiguous. So yeah, since it never reallocates, the pointers are always valid after growth. And VirtualAlloc handles my alignment, and it also handles my zeroing out of the returned memory, which is pretty useful. Basically, you're going to allocate. I just double it in size. That's what I do on allocation. And the begin pointer is never going to change. Useful. All right. Iteration is branchless. It happens through operator ++. I don't give you the square brackets operator. I was going to give you access to .data, but then I kind of realized it's not useful. For the same reason I don't give you operator square brackets. You can point to like invalid or erased elements, and the data is unordered, so it's not really useful. All right, you traverse the main array and the parallel skip array at the same time in the iterator. Colony doesn't do it that way. It interleaves the skip array with the main data, and it's a 16-bit pointer, 16-bit integer, versus my 32-bit integer, because mine is contiguous. Anyways, the skip array is going to store the gap in indices between live elements. So if element 0 is live and element 10 is live, then there is going to be in the skip array a 9 to tell you to jump ahead 9 if all those elements in between are erased. All right, anyways, this is the operator. I mean, you can see how simple it is. It's branchless. Basically, we're going to increment skip pointer, we're going to increment data, and we're going to increment them by what skip pointer is pointing to, which is a 0, so they don't get incremented. All right, anyways, we increment skip pointer, we increment data. Now, free list is an empty slot. We hold the free list nodes in the empty slots. Obviously, there's no element here, so we don't want to be pointing here. Luckily, skip array tells us that we don't want to be pointing here. We should skip this slot. So we increment them by what skip array is pointing to, and we skip it. Branchless. All right, now we iterate normally. We don't skip. We iterate. We skip 3. There you go. Relatively simple. Now it's bi-directional because that just helps some of the logic, and it lets you go in reverse. I don't really have a use for going in reverse, but it helps some of the logic elsewhere in the container. Now skip array, it's kind of updated on erase and it's rewound on insert. You're going to see what that means later, but basically we go back in time instead of recalculating anything. And yeah, there's sentinel indices in the skip array in order to basically prevent out of bounds access. All right, erase works like this. Let's just imagine the free list initially points to this slot. We're going to erase this element here. We're going to check the left and the right element. We're going to store them in a free list node. We're going to check this element right here that's ahead because this is a block, right? Since we say that there is 3 elements to skip here, we know there's going to be another 3 right here. All right, this is how we update it. Basically, we take this free list node, we put it here, we replace the user item, and we update the skip block right here. So the skip block went from a skip block of 3 to a skip block of 4, and we store the left and the right elements, the left and the right skip block in here. All right, and we repoint the free list node pointer. All right, and then this is pointed to here. All right, now we're going to erase this, and we're going to have to combine this block of 1 with this block of 4, and it turns into a block of 6. And we take the left and right element and we store them here. And this is how it's pointing now. So erase is relatively simple. This is not how the code actually looks. I kind of updated the code since this presentation, so we'll take a look at that. All right, now insert, let's just imagine this is how the free list node or the free list is pointing to at the moment. All right, on insert, we are going to insert where the free list was pointing to. So the free list was pointing here. Let me go back and show you that. Free list is pointing here. We're going to insert into that slot. So it's a last in, first out stack, basically. That's what the free list is. We're going to take the left and the right stored indices. We're going to put them in the left and the right slots. We're also going to jump forward and put it in this slot. So we can update this 6 to a 4. And you can see we just kind of rewound what we did. All right. We set this to 0 and we put the user type here. All right, now we repoint the free list and it points like this now. All right, now if we insert here again, we're going to update it in this way. Take the left and the right elements, put them where they're supposed to be. Pretty simple. That's not how the actual code looks. I changed it slightly. All right, my girlfriend drew this. My inspiration was Matthew Bentley for this container. I figured I should leave it in since she drew it. That'd only be nice to her. Let me go and show you the code roughly. Now I'm using concepts in order to give you a tag, whether you want to use generations. If you use generations, you're going to get a couple of like, you're going to get this generational handle versus a normal pointer on return from insert. You're going to get this generational node with a generation versus this individualistic node. That's just a template parameter. Let me see here. So yeah, a couple of constructors. Insert, obviously. Erase. A couple of helper functions. The size, if is alive check, is 01. Now on Colony, it's not 01, so you're going to see the performance on Colony is kind of bad. And it's also going to require a double if you use it in any actual real world scenario. So, that's a benefit of this container. Yeah, you can reserve. Compress will take all your elements and it will, defragment the container and put them all in the beginning so you have no holes. And it's going to zero out everything past the last element. So that's going to invalidate all your pointers. All right, shrink to fit is not going to invalidate your pointers except everything past the last element. It's going to invalidate anything that points to those elements. It just kind of decommits the pages. So you're going to save a little bit of RAM. All right. Here's your iterators. Here's the implementations. This is allocate. If you want to copy a vector, generation. I feel like this is a bug. I feel like this shouldn't be this way, but I'll look at this later. All right, anyways, deallocate, decommitting pages, getting allocation slots, growing. Now here's if you want to go back in time and rewind your skip array on insert. And here's the logic for erase, essentially. Yeah, here's some members. The code is kind of complicated. Oh, my dad is calling me. I should take this call. Call him back after this. All right. Let me do a quick benchmark. So we're storing 2 cache lines. That's the size of the type. It's 3 million elements. Let's see. So the performance, it is faster to check if it's alive. It is faster on allocation. It's faster on iteration. It's faster on removal. It's faster on sparse iteration. It's faster on reinsertion. So yeah, it's faster in every scenario. Now it's not 01 for colony for the is alive check, for the active check. So it's just pretty bad in terms of performance. Yeah. Now it's not a good benchmark, but I'm using MSVC, and if this was my job, I would actually benchmark it, properly. But it's a good enough benchmark to prove that it's worth benchmarking at the very least. If it was my job, I get GCC, I make a nicer presentation, and I would cut out the stutters in this video and cut out this clip of me ending the video. Bye.